Okay, so we are studying several rank statistics. We have defined the needs of rank statistics in non-parametric um, inferential problem, and also last couple of classes we have discussed uh, Spearman rank correlation and Kendall's tau. Okay, and well, we have done the test of significance as well, which is most important while you are dealing with inferential statistics. Now, one annexure of previous lecture can be presented herewith. I have named it as a part B of lecture 4. Why, you will understand. This is some sort of theoretical aspects on the rank statistics. Okay, but as we have made the structure of this course not to be deeply rooted mathematical derivation, I try to keep the essence of this annexure part, which is otherwise termed as part B, as far or as easy as possible. Just few informations I am going to share with you just for your own concept building, so well, let's start that lecture. Linear rank statistics. So as you can see by the name linear rank, so it is a function of ranks. This statistic, what is statistic? Statistic is a function of sample observation. When I am saying rank statistic, that means function of the sample ranks. You have n observations and you are doing with the functions of those, ranks of those observations, right? Now, when I'm saying linear rank statistic, that means I'm trying to make a linear function based on the ranks of the observations, right? Now, most of the non-parametric test statistics are the special cases of linear rank statistic. What is linear rank statistics? That's what our primary concern right now. We have seen the joint distribution of ranks is independent of the underlying population. Therefore, in constructing distribution-free test procedure, ranks will be the cornerstone. Already I told you. Commonly used non-parametric tests are expressed in terms of linear combination of the function of ranks. So linear combination means I am talking about the straight line, not in the two-dimensional place, but it's a n-dimensional vector space. Clear? Because you have n observations. So when you have n observations, you have n corresponding ranks, right? And you are clubbing them together by a linear function. That means you are indicating towards the straight line defined in the n vector space. Clear? So these linear combination is called linear rank statistic. Let x1, x2, xn be a random sample of size n with the corresponding ranks r1, r2, rn. Then r1, r2, rn follows a discrete uniform distribution. And what is that probability, joint probability mass function? Already we have seen that probability r is equal to small r. R means, here r means r1, r2, rn. You can understand that I am writing r in terms of a vector, and that's why I am giving that underbar. Underbar means I am indicating towards a vector. Vector of how many components? Vector of n components. And smaller is a value taken by that vector, capital R. This is the random vector. I can say this is the random vector. Now the random vector can take any value. So suppose for R1, the rank of the first observation may be 5, the rank of the second observation may be 1. So for a specific small r, the probability distribution is 1 by n factorial. Earlier in some lectures, I have mentioned this. What is n factorial? That is n into n minus 1 dot 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 into 3 into 2 into 1. Just a quick reminder. Now L, which is the linear rank statistic, is just the linear combination. You can see that L is summation AI into BRI. So AI is your constant. We will call it as a regression coefficient. You people are aware or familiar with the name of regression, statistical regression. So these are constant, regression constant, in other way termed as, and into BRI. BRI means this is the function of the ranks. So for the simplest case, what we can do, we can just take BRI is equal to the rank of ith observation. In that case, and AI is equal to 1. You see, look at this example. This is the simplest case or the trivial case. Take all AIs are 1 for all I. If your observation x1, then also you are taking A1 as 1. If your observation is x2, your A2, this regression coefficient will be 2. Similarly for AN, this is also be 1, and AN, this also be 1, and BRI is the rank of that particular observation. Then the form of linear rank statistic will be L summation Ri, that is sum of all ranks. Therefore, this L, this is a particular case of linear rank statistics. Okay, as I have already told you that AIs are called the regression coefficient and BRIs are called the scores. So a linear rank statistic can be identified by its regression coefficient and its score. Clear? Okay. And linear rank statistics are used for a number of hypothesis testing problems. You have to remember the Spearman rank correlation or Kendall-Stau, everything is a special case of linear rank statistics. That's why I am giving you the flavor of linear rank statistics in this course. Replacing the original observations by the ranks surely results some loss of information. However, that loss is not significant. You might understand that, well, when I am replacing one observation by the corresponding ranks, am I not losing some information? Yes, we are losing some information. The information bore by the observation itself. But this loss, it can be proved that this loss of information is not so significant. Rather, replacing the observation by the corresponding ranks and henceforth constructing the linear rank statistic will give a smoother way of working out testing of hypothesis problems. So that's why this replacement of ranks is permissible in case of non-parametric statistics. Okay. Also, the expected value of L. What is L? The last slide we have seen, L is this part. So, of course, this is a statistic as it based on the rank, and the average or expected value of L is n into A bar into B bar. What is A bar? A bar is the mean of the regression coefficient. B bar is the mean of the score variables. You just remember this. For linear rank statistic L, if AI plus AN minus I plus 1 or BI plus BN minus I plus 1 is constant for all I, the distribution L is symmetric about its average. Average means this. So what is that? That is, suppose you have n observation. So if A1 plus AN is equal to C, and say A2 plus, just replace I by 2. 2 means the second observation. Clear? So AN minus 2 plus 1. that means a n minus 1, that also C, then the linear rank statistic L will be symmetric about its average. Most of the time, next lecture we are heading for Wilcoxon sign rank test, sign test, Mann-Whitney test, so many test statistics we are going to introduce. Most of the cases, those statistics maintain these condition, that condition ai plus a n minus I plus 1 is equal to C. And that's why these statistics are symmetric. And what is the benefit of having a symmetric statistic? The benefit is you can count, you can make your rejection region either from the left hand side, either from the left tail or from the right tail. The similar idea you have encountered while doing the test using Gaussian structure. Gaussian structure means normal structure. The left tail probability of rejection remains the same with the right tail probability of rejection, right? Can you make the match with this? So symmetry in the context of test bears a heavy importance. Under some conditions, and these conditions are related to the probability convergence theorem in statistics, we are not going into that detail. L minus expectation of L divided by square root of variance of L, that means it is the standard deviation, and it converges to normal 0, 1. That means the asymptotic distribution of the linear rank statistic is also normal 0, 1, standard normal. So that's it. You can go for reference fundamentals of statistics, but for this linear rank statistic, J.D. Gibbons' book, as I have already mentioned in my earlier lecture, J.D. Gibbons' book, J.D. Gibbons' non-parametric inference, that book is more meaningful or more informative. Okay, thank you.